Today we are talking about chapter 7 and 8, which are all surrounding chemical bonds. So a chemical bond is the attraction that exists between the positive nucleus on one atom and the negative electrons on a neighboring atom. And the interaction that those two atoms engage in based on their mutual attraction and the number of electrons in their valence shell. So the valence shell very often determines what type of bond an atom will form. And so as we have spent the last few weeks getting a really in-depth look about the internal structure of the atom, the protons, the neutrons, the electrons, the isotopes when the neutrons change, the ions that form when the electrons change, now we're going to be moving forward to look at how do those atoms interact with one another and how do they behave when they come into contact with one another in the natural environment. So we really start this conversation with the octet rule, which you may remember from our previous chapter. The octet rule tells us that atoms tend to form compounds in such a way that the atoms will achieve a stable octet of electrons in their valence shell. Octet, remember, means 8, right? 8 electrons in their valence shell. So when an atom is in its lowest energy conformation, for most atoms, that means that they have filled their valence shell with 8, exactly 8, and only 8 electrons in that shell. So atoms achieve this kind of atomic perfection by gaining, losing, or sharing electrons. This first image here is showing us how an atom might share an electron in order to get 8 electrons in its valence shell. So what we're going to do is start by counting the orange electrons on this first oxygen atom. So we start over here and we count 1, 2, 3, 4, 5, 6. So oxygen is 2 electrons short. It has formed a bond with a neighboring oxygen atom to give it 7, this blue one, and 8, this blue one. Those shared electrons end up counting for both atoms. We count the valence electrons on the blue oxygen atom. We can start back here and say 1, 2, 3, 4, 5, 6 blue ones, and the 2 orange that are in the bond makes 8. So both of these oxygens have achieved a stable octet by sharing electrons. Another option is to gain or lose an electron in order to get your valence shell. So on the left here, we have a sodium ion, and in its outermost shell, it had 1, 2, 3, 4, 5, 6, 7, 8, but it had this extra electron here, which made it no longer a stable octet. It just had 1 electron in its valence shell. On this side, we see a chlorine atom that has 1, 2, 3, 4, 5, 6, 7 electrons in its valence shell. Almost 8, not quite. And so what we end up seeing happening is the sodium donates this extra electron over to the chlorine atom, making the chlorine a negative ion because it gained an electron, while the sodium becomes a positive ion because it lost an electron. And these are concepts that we've talked about before, but now we're looking at them from the perspective of what happens next. How do these bonds start to form, and how do they impact the natural environment around us? So ultimately, there are 2 main types of bonds that can form. The first kind is an ionic bond, and it occurs based on the formation of 2 ions. So remember, the cat ion is the positive one because cats have paws, and the anion is the negative ion. Once you've gained an electron, you become more negative. And what happens after that, once we have our positive ion and our negative ion, or our cat ion and our anion, those two atoms now electrostatically attract. They have an electromagnetic charge. It's going to pull them together like magnets onto a metallic board or magnets onto a refrigerator. They're going to be attracted and then they're going to stick together. And so we call this the strongest type of bond. Now, this is an interesting point because in biology, we say that covalent bonds are the strongest. And in chemistry, we say that ionic bonds are the strongest. And I want to explain to you why. The kryptonite for an ionic bond, the one thing that can pull an ionic bond apart without any problem at all, is water. You may realize that biological systems like you and like me are rich in water. They're full of water. And so because of that, ionic bonds in a biological system are rather weak. In chemistry, though, chemistry doesn't just occur in biological systems or even just on the planet Earth. I mean, if you think about the planet Earth in conjunction with the entire universe, it's so small, and so are we. And so from a chemical perspective, ionic bonds are the strongest because the universe is quite dry. There's not a lot of water around. So this may be contrary to something that you learned in biology to say that ionic bonds are the strongest type of bond. But for chemistry, because chemistry is so dry, that is the truth. Covalent bond is the other kind of bonds that we see in this setup. Covalent bonds result from the sharing of valence electrons. And that sharing is maybe a bit of a stretch. It's not exactly a nice, even share like we think of, like cut the cookie in half and everybody takes half and they're so happy. It's really more of those covalent bonds result from a lock in the battle to the death, gripping the electron, trying to rip it away from the other atom, but not being strong enough. From the outside, it might look like a share because the electron kind of stays between the two nuclei of the two atoms. However, in reality, if you zoomed in on what was happening with those electrons, both atoms are grabbed onto the electrons and they're pulling them towards themselves as hard as they can, much more like a game of tug of war than sharing. But we'll come back to the visualization of what a covalent bond looks like a little later on in the lecture. Most bonds are between these two extremes. So in most cases, we don't have this even perfect 50-50 split. But also in most cases, we don't have this full, complete, removed transfer of the electron. Most of the time, we see something in between those two extremes. And there's definitely a spectrum of bond characteristic. You can be really ionic or a little bit ionic or a little bit covalent or really covalent. And so there's definitely a spectrum of bond creation. And we're going to be looking at that spectrum as soon as we get an understanding of the relationship between the types of bonds. So this is a little concept map of the main things that we are going to be talking about during this chapter. We've touched on some of them already, but we're going to get back into each of them with a lot more detail. In chapter 8, which is actually what we're covering first, we're going to be taking an in-depth look at the covalent bond, that share, which remember really is like that tug of war battle, locked in battle to the death for the electron. We're going to be looking at that interaction, which we call the covalent bond, and whether or not one team is really stronger than the other and kind of winning, which creates something called a polar covalent bond, where we have kind of someone way out in the lead and someone kind of falling behind in the struggle for the electron. Or if that sharing of the electron is really, really evenly matched, in which case we call it a non-polar covalent bond. So we're going to be looking at the two types of covalent bonds. Once we understand these two types of covalent bonds, we'll then move on to the ionic bonds before we wrap up for the semester. The first type of bond we need to look at is an ionic bond, and this is the one you're probably most familiar with because we have talked about ions and ion formation, cations and anions, kind of at length. So the ionic bond is not a big stretch. what we do when we create an ion is we create a cation, which is positive, and an anion, which is negative. And then they're going to attract each other like magnets because opposites attract, and they're going to stick together. In this case, only one of them has electron density. When you see a model like this is called a ball and stick model here because it shows the two different atoms in the center and then it shows the bond connecting them. This is an electron density model because it puts this electron density around the outside, kind of showing us the relative size and the amount of electrons that are around those atoms. So the chlorine ion has gained an electron, so it has all of the electron density. So we see this negative charge here on chlorine, and we also see this red sphere surrounding chlorine because that's indicating that chlorine has all of the electrons. It's like a hot cold of where is the electron. So like your warm, hot heat over here, and over here on the far side of sodium, you're ice cold. That electron has left sodium. This doesn't tell you whether or not they're happy or sad. Sodium is very happy with its situation here. It gave up the electron that was keeping it from a stable octet. Chlorine is also very happy here because it gained an electron, giving it a stable octet. All this tells us is where are the electrons. And so we see from this model that the electrons are over here around the chlorine atom. As mentioned before, the next type of bond is called a non-polar covalent bond. So I'm going to ask you a silly question. What is in the North Pole? Hopefully you said Santa. Santa's in the North Pole, right? And what's in the South Pole? Not Santa. That's all that really matters for this story. The North Pole and the South Pole are different. When something is polar, if you've ever heard they're polar opposites, or oh my gosh, they're bipolar, it means that they live within two extremes, or they are two extremes. If two people are polar opposite, then one is an introvert while one is an extrovert, and one likes sports and the other one hates sports, and one eats only junk food and one is a clean eating vegan. Polar opposites, right? So if a molecule is polar, then it has two regions that are very different. But if a molecule is non-polar, which is what we're talking about here, the entire molecule is pretty much the same. So this is a picture of the non-polar covalent bond between two chlorine atoms. And what we see, so we have our chlorine atoms on the inside, but what we're seeing around the outside is this kind of same color all the way around, this kind of greenish yellow color that is indicating that the electron is evenly distributed all throughout the molecule. So this is a molecule where there are no regions of positive or negative. Not only not ions, but not even a difference in pull. This is an exact even share. To the morsel, to the crumb. This is an exact even share of that electron. That's because the two chlorines that are pulling on it are of equal strength. Imagine being in a tug of war with a person or with yourself that is exactly evenly matched to you in every way. You're not going to see any sort of lead or any sort of winner. You're just going to see this kind of locked, right? Imagine like an arm muscle that just stays exactly at the top. We're not seeing anyone with the advantage. That's what a non-polar covalent bond is. So I bet you can imagine that a polar covalent bond indicates a time when there is one that is stronger than the other, when there is a winner emerging or someone in the lead. In a polar covalent bond, we see a difference in strength between the two atoms that are attached to that electron, that are pulling the electron. This unequal strength leads one side to be winning while the other side is losing. So if we look at this hydrofluoric acid compound, what we're going to see here is, remember, red, hot heat, right? Red is where we're finding the electron density. So we would expect the electron density in hydrofluoric acid to be over here. And we would expect ice cold the electron density to be missing from hydrogen side. So we can draw this arrow that points to where the electron density is. So it's going to be pointing to the red zone. And we remind ourselves of that by making this convenient little plus sign with the back side of the arrow, because remember, electrons are negative. So if the electrons are found over here in the red zone, then that is where the negative charge is in the compound or molecule. Good news, I will not be having you draw or come up with dipoles or dipole moments like this. I'm just telling you about a kind of annotation that books use that might help you when you're looking at figures or looking up things online. This is another space-filling model of an atom. So what's inside of this little egg here is a carbon dioxide. So a carbon in the center and 2 oxygens on the outside. And so what we see is that the oxygens are the hot heat, right? The oxygens have the electron on the outside, where the carbon in the middle is icy cold. So in the center of this molecule, we have an area that's lacking electron density. So that would be the positive region, the blue positive region. And on the outside of that molecule, we would have 2 different negative regions, both surrounding atoms that have really attracted the electron out to those edges of the molecule. So all together now, we have talked about ionic bonds where we have a complete transfer of electrons, polar covalent bonds where we have an unequal share of an electron resulting in positive and negative poles or regions of the atom, and we have non-polar covalent bonds where the electron is evenly shared and evenly distributed all throughout the molecule. Now we can generalize and guess what kind of a bond will form based on the identities of the atoms, but we don't want to generalize. So in our next look at these kinds of bonds, we are going to be determining the type of bond by simply looking at the difference in their electronegativities. Remember, electronegativity is how strongly those atoms are able to pull on an electron. So when we look at the difference in the electronegativities, kind of like looking at sports stats, we can make a prediction about which atom will win the electron when they come into an interaction. So will one atom be able to pull the electron completely off, forming an ionic bond? Will it be able to pull the electron over but not away, which would form a polar bond? Or are those 2 atoms going to be locked in a perfectly even share, perfectly even match, where we would form a non-polar covalent bond? So the next time we meet up, we'll add numbers to this idea and we'll get a numerical or quantitative way to determine what type of bond will form between any 2 atoms on the periodic table. I'll see you then.